By the end of this video, you'll be able to fine-tune a small and fast multimodal text and speech language model, and you'll be able to deploy a server so you can put that model into production. By means of a very small demo, you could head over to Wikipedia, grab any image. Here I'm going to copy the image address for this frog, and I'm going to paste it into a curl request for a server that I've set up. So just in here, I'll put in the image URL. And I also have some text here. I'm asking what's in this image. And now I'll copy all of this curl request and head over to a terminal, paste that in, and let's see what the language model comes back with. The image features a close-up view of a frog sitting on a rock. The frog is brown and grey in color with a large head and small body. It's positioned on the rock, which is covered in moss and appears to be wet. The frog is facing the camera, giving a clear view of its features. So let's just see if that seems to roughly match. I mean, maybe not perfect, but this is a model that is really small. It's only a few gigabytes in size. It's called Moondream, and it's based on a small language model, Phi 1.5, combined with a vision model. We're going to see the architectural components of that model. I'll go through each of them at a high level and then in code. Then we're going to do some fine-tuning on a custom data set. I'm going to fine-tune it on some chess photographs, as I did previously for my video on the Lava multimodal model. After that, I'll show you how to set up a server and how to deploy that into production so that you can make queries, both individual and batch. So for overview, let me give you that high-level framework of how Moondream works. I'll talk about some of the specifics of that design and then talk about using a LoRA approach for fine-tuning it. I'll go through a notebook demo of that fine-tuning, and then I'll deploy the Moondream server. For a bonus, a few notes on a vLLM integration that's hopefully coming up, then a few notes on training models from scratch, training a multimodal model from scratch, starting with pre-trained language and vision models. And then I'll talk a little bit about fine-tuning datasets, the Lava dataset, and also a new one called the Cauldron. So let's get started with the high-level framework of how this multimodal model is built. Multimodal models are basically a combination of a language model and a vision model. So you have a vision encoder here, and that is going to pass embeddings or vectors representing the images into a language model. And the language model will receive the vectors from the vision encoder, but also receive the embeddings that are coming from the text, like the question I put in, what do you see in this image? So we're going to combine a language model that has already been pre-trained, Phi 1.5 in the case of Moondream, with a vision encoder that has already been pre-trained. Now for these to work well together, the size of the vectors or embeddings that are being passed from the vision encoder to the language model need to be the same size as what the language model expects. So if the language model expects each of these vectors to have a dimension 2000, then the vision encoder would need to produce a dimension of 2000. But typically it's hard to find a vision encoder that will exactly match with the embedding size of the language model. So what we do is we put in an adapter. And this adapter here both ensures that the embeddings are adapted from, say, a lower dimension of 1000 up to the higher dimension of 2000 to fit the language model. But also it provides the function of adding some trainable parameters that allow us to kind of mesh better how the vision encoder is working with the language model. Now, I should note that when it comes to tokenizing the text, it is tokenized as we typically would do with the tokenizer, say, that we use in Llama 2 or Llama 3. So the tokens of the text are converted into vectors, as typically we would do with a large language model. The key is that we also want the outputs of the vision encoder to be in these vector forms so that they can represent information that is input in the same manner to the language model here. Now, before I move on to describe the specifics of the Moondream tiny model, let me talk about how the vision encoder works. So the vision encoder takes in information about the image and it converts it into vectors. And the way it works is by breaking the image into patches. Here we have an image and it has 4 patches. And the goal of this encoder is to convert each of those patches into a vector that represents its meaning. So the first step is to gather all the information that's within the patch. Say we have a patch here with 14 by 14 pixels, which is what we have in the Moondream model. So we have the information from each pixel, which is a magnitude for red, for green, and for blue. And then we also have the position of this patch. So here it's in the top right. So the first thing the vision encoder does is it takes the image pixel info, the red, green, and blue, and the patch position, and converts that using linear layers or multi-layer perceptrons. So it converts that using trainable parameters into an input vector. So you have an input vector that represents this patch, and likewise you'll have an input vector representing each of the other 3 patches. And now we take these vectors and we pass them through a vision transformer. And this is a multi-layer neural net. It includes attention. It might have, say, 27 layers, I think, in the Moondream vision transformer. And the goal of this transformer is to take the embeddings representing each patch and convert them into some meaning about the overall image. So you'll have these embeddings that come in, and then you will have output embeddings, typically the same number of output embeddings as there are patches. And these output embeddings, which represent meaning, they will be fed into the language model in addition to the text, which is being tokenized. So this here is the vision transformer, and its goal is to provide vectors that are fed into the language model in combination with the input text embeddings. These then are fed forward through the language model itself, which has got multiple layers and is a transformer, and that allows you to predict what the next token is going to be. So let's move on to the specifics of the Moondream formula. And I want to talk about the 3 parts. So I'll talk about the vision encoder, then I'll talk about how the adapter is designed, and then I'll talk about the language model. So I'll talk about the vision encoder, the adapter, and the language model here. So the first part is the vision model. It's called SigLIP. And this pre-trained vision model, so we're taking some pre-trained weights and just inserting them into the overall architecture. It supports images that are 378 by 378 pixels in size. And this is broken into 14 by 14 pixel patch sizes. So if you divide 378 by 14, that means you've 27 patches in the width and you've 27 patches in the height. And 27 by 27 is 729. So that means we have 729 input embeddings. So if you look back here at what's going into the language model, there will be 729 of these image embeddings. And then on top of that, there will be the token embeddings right here. Okay, so 729 input embeddings. And then because we have 3 colors, red, green, and blue, every patch has got information for each of the 14 by 14 pixels times 3 for each of the color channels. So there are 588 inputs per patch. And then plus there's also going to be the positional info. So I'll just say positional, but there's also information on where that patch is positioned within all of the 27 by 27 patches. So this information here is converted into a vector using some trainable parameters, which is typically a linear transformation of the inputs plus the positions. And once we have a vector representing each patch, we take all of those patches and pass them through a 27-layer transformer. So this is what is happening in the Moondream vision formula. And actually, if you head over to the Moondream repository on Hugging Face, you can take a look at the vision encoder file. So just within the files, you can open up visionencoder.py, and let's see if we can find some of these numbers that I just mentioned. So first of all, let's take a look for the number 14 because that's the patch size. So here you'll find that within linear patch embedding. So this is converting the information on the input pixels in red, green, and blue, and it's converting that into a vector. So here you can see the patch size 14 by 14. You can see C here, which is the number of channels, red, green, and blue. And ultimately, we're going to create a matrix that is going to be C by P1 by P2. So the representation of each patch is going to be red, green, blue times 14 times 14. So this is how we are setting up the patches, and we are applying a linear layer. So you see self.linear. This means that we're going to set up a linear layer of trainable parameters so that we can convert from the pixel color information into a vector. Now, you'll remember that we need to add on the positions. So I remember from the code, we're going to want to add in the positional information to the embedding information. So here, if you look at the forward pass within the Vision Transformer, you can see that the first step is we get the patch embeddings. So we convert the color information into using a linear layer into a vector, but then we add on the positional embedding. So here we have positional embedding, and the combination of the information on where the patch is with the colors within that patch then allows us to convert into a vector representing that patch. So actually, if I look up position embedding, just POS embed, you can see here that positional embedding is actually just set to some randomized values representing the position. And this information then, it is going to become trainable during the process so that we can train the vision encoder to encode information on the position of the patch and how that influences the overall meaning of the entire image. So there we have the positional embeddings, we have the patch embeddings, and the next thing I want to show you is how the embedding for a given patch combined with the embeddings for the other patches is then transformed into a form of meaning. And that's done through the Vision Transformer, which is made up of a series of blocks. So we have 27 of these blocks in the Vision Transformer, and you can see that the first part in that block is going to be an attention layer. So we're going to do attention between the patches. Then we're going to do a multi-layer perceptron layer, which is a sandwich of a linear layer with a norm and then a linear layer. I'll show that again later. But basically we have attention, we have multi-layer perceptron, and then we have two norm steps that are going to be included. Basically, as you can see in the forward step here, we take the input embedding for the patch, we apply attention, we norm first and then apply attention, and then we take that result, and what we do is we norm and we do the multi-layer perceptron. So this is the application of the attention and then the multi-layer perceptron. That's the forward pass through one single layer of the transformer, and that's going to be repeated 27 times. So this is how we do the forward pass through the vision model. Just one note that you're probably wondering, well, what if my image is not 378 by 378? Well, Moondream will just resize the image using averaging. It uses bicubic averaging. And if the image is not square, well, it forces it to be square. So if it takes a rectangular image, it's just going to squash everything into a 378 by 378 image. Now, there are pros and cons to this. It's quite simple, so that's kind of nice. But there are other approaches where you could alternatively make multiple large images out of the single one. You could maybe represent a horizontal image as two square images. So there are many approaches you could look at, but Moondream just takes a simple approach of averaging and squashing. The second piece of the architecture to talk about is the multi-layer perceptron adapter, or what's called vision projection in the code. So what I'm talking about now is, how do I take the embeddings that represent the meaning of the image? How do I take those, and how do I both adapt and resize them so that they're appropriate to feed in as information to the language model? So this is the adapter here. And we have a few points on this. So the input is 1,152 dimensions. That is the dimension of the output vectors from the vision encoder. And what we need to get that to, we need to get the output to 2000, because the input to the Phi 1.5 model is expecting vectors of size about 2000. So basically what our adapter is doing is taking in inputs of 1000 and outputting vectors of 2000. Now, it doesn't directly go from 1000 to 2000. That would be called a linear layer if you just simply went from 1000 to 2000 via a single matrix of trainable parameters. And you could do that. And actually Lava 1.5 did that, and it probably works okay. But using a multi-layer perceptron is a little more complex, but gives better performance. So what the multi-layer perceptron does is it first will cast the 1000 dimension up, and it will cast it up to about 8000, so 4 times 2000. It will then apply an activation function, and then it will project it back down to 2000. So let's see that written in the code. I think I can just search for vision projection. Here we go. So the image embedding dimension is 1000. The model dimension, that's the language model, is 2000. So we need to get from here to here. And we're going to do that via a hidden state in the middle. So a sandwich with 8000 in the middle. and we're going to do it by means of an MLP, which is a multi-layer perceptron. And we can see exactly how that multi-layer perceptron is designed by looking at its definition, which is right here. And the multi-layer perceptron takes in 3 inputs: the input features or dimension, the hidden features, so 8,000, and the output, which is about 2,000. And what it does is it first applies a linear layer to get from about 2,000 up to 8,000. Sorry, it takes it from 1,000 up to 8,000. Then it applies an activation function, it's GALU here, and then it will take it from 8,000 back down to 2,000. So you've got these steps. It's taking in 1,000, 8,000, and then 2,000 is the output. So that's the MLP layer that's sizing the vision encoder so that it matches onto the language model. And that leaves us to discuss our language model itself, which is the Phi 1.5 model. There's not a whole lot further I'm going to say here. It's a transformer, much like Llama 2 or what OpenAI uses for GPT. It has a tokenizer to convert the text into vectors for each token, and then these inputs are taken along with the embeddings from the adapter. And then we go through this autoregressive decoding process in order to generate the next token. And you can look in more detail if you really want to at the Phi model. It's defined in the modeling Phi file within Moondream. And it's a fairly long file that describes how the transformer is built, but it includes, as we would expect, attention. It includes then interspersed MLP layers, and you've got multiple repetitions of that. So I think it's 24 layers then of the combined attention plus MLP. And that brings us to a complete description of our architecture here for the Moondream model. It's of course a very compact model because Phi is 1.5 billion parameters. So in 16 bits, that's about 3 gigabytes in size. And the vision encoder is, I think, less than 1 gigabyte in size. So this is a very compact model, but I think you'll be impressed by the performance. So following along with our overview here, the next step is to talk about how we will fine-tune this model. And because it's a small model, you could just do full fine-tuning. There's actually a script. If you take a look at the GitHub repo here for Moondream, you can find a fine-tuning script that will allow you to update all of the parameters. And that works because it's quite small, so you don't run out of VRAM too much. But what I'm going to do is I'm going to use LoRA fine-tuning, which I use a lot in the Trelis research videos. Rather than updating every trainable parameter within this entire architecture, I'm going to apply LoRA adapters to the linear layers throughout all of the architecture. So I'll freeze all of the base weights when I forward pass, and when I backward pass, I'm only going to update these 2 smaller matrices that together, when multiplied, if you did, say, B transpose A, if you multiply these 2, you get back to a matrix that's this size. And at the end of training, I'll just combine and merge these 2 matrices to have a final trained matrix. So the adapters are going to be applied to the linear layers all over the place. So I'm going to apply them to the linear layers in the vision encoder. I'm going to apply them to the linear layers in the MLP. And I'm going to apply them to the linear layers in the Phi 1.5 model. And this will reduce the VRAM that we need for training because we have a much smaller number of trainable parameters than when we train the full model. So this will reduce significantly our VRAM because we only need to store the gradients and optimizer states for a much smaller number of model parameters. So let's move on, and I'll walk you through a notebook demo of how I do that fine tuning. And I have adapted some of the code that you'll see within the GitHub repo, specifically so that I'm able to do this LoRA fine tuning. And I've also added in some of the steps that I typically would add in the Trelis research fine tuning type scripts. So let's head over to Trelis research. You'll be able to find my customized scripts in the advanced vision repo, which is available for purchase if you go to trelis.com/advanced-vision. Now, in this, you've got a few things. There are the fine-tuning scripts for fine-tuning LoRA. And additionally, you're going to have scripts for running a server. This is a custom server that I've built that does support batching. And I'll show you a little later how to run that. So in the fine-tuning branch, you will see there are a number of scripts available, including from my past video on Lava and on IDFix. I hope to make a video soon covering the latest IDFix model that has just been released, but today we're focused on Moondream, so we'll be taking a look at this notebook here. And to run this notebook, I'm going to make use of a RunPod one-click template. So I'm just going to go to this RunPod one-click template here, and I'll open that up. And I'm going to click deploy, and then what I'll do is upload the IPYNB notebook that I just showed you for doing the Moondream fine-tuning. So here you'll see I'll pick an A6000. You could easily fine-tune on something much smaller because this is such a small model. And you'll see that this is opening up my default fine-tuning notebook with CUDA 12.1. So I'll just click on deploy here and I'll get the Jupyter notebook started. So here I am in the Jupyter notebook and I've got Moondream fine-tuning opened up. There's a series of installations that need to be run, including transformers. Note that you'll need to install parameter efficient fine-tuning, PEFT, because we'll be doing some LoRA fine-tuning. So with that done, and I like to install HF transfer for rapid weight download, although the weights are going to be really small here. You can use that by setting the HF hub enable HF transfer flag to 1 environment variables. Now, we're going to move through this step by step. We're going to load a data set. We're going to run some evaluation on the model. You can run it in quantized form if you wish. Then we're going to set up the LoRA adapters. And once the LoRA adapters are applied, we'll then be able to start the training. So we'll run the training. And once training is run, we're going to run evaluation. So here I'm just applying the adapters. I'll go through this in more detail. We'll run the training, and then we'll run evaluation of the model again after the training and see how the model performs on a series of chess piece examples. The dataset I have is the Trelis chess pieces dataset. It's public if you want to take a look at it on Hugging Face, and it's simply a series of pictures of different chess pieces I have at home and the names of those chess pieces, so we can fine-tune it on the captions. So here I'm just loading this dataset. You could load any dataset that has images and captions within it. It just needs to have an image column and then a caption column here. In fact, why don't I just show what that looks like? Let's go to Trelis chess pieces and take a look. Take a look here at the viewer. So yeah, we just have a column of images and then we have a caption. So here like is a white rook and here is a white rook. Okay, so here what I'm doing is defining my data set, and I'm making sure to load the image. So I'm returning this object here that has an image, and it also has a QA, which contains both a question and an answer. And I'm loading a train data set and a test data set. I've already on the Hugging Face hub, I've got 2 splits. So I have train and test, which I can use for validation purposes. So once my data set is loaded, I'm now going to move to load the Moondream model. So the loading of the Moondream model, you can find details just on the Moondream repo on Hugging Face. Notice that it is possible to load it using 4 bits. So you can load it in NF4. I will say that for this small model, I definitely see a degradation of performance when I use quantization. So I'm going to train the model here without using quantization. And since it's quite a small model, that's really not an issue for VRAM in any case. So here, loading the model, loading the tokenizer, and then just printing out the dataset, printing out row 0. You can see that it contains an image, and it also contains this QA, which contains the question, what do you see? And the answer, a single white rook. So just checking the dataset was loaded correctly there. Now next, I'm going to set up the LoRA adapters. And to do that, I want to see what my model architecture is. So I'm just printing out Moondream. And this is nice because it's going to show us what's within the model. So first off, you can see here, there's a vision encoder. And this vision encoder, it's got that linear patch embedding that we talked about earlier. So a linear layer that takes in 588 features, which is the 3 red, green, blue multiplied by the 14 by 14. So that's the input features per patch, and then it converts it into a vector for each patch of 1152, so about 1000 dimensions. Now I can just increase my screen a little more. So after that, you have the vision transformer that takes those embeddings and converts them into a meaning. And you'll see there are very many blocks here, and each block is comprised of an attention portion and then a multi-layer perceptron. And because I've applied LoRA actually, because I ran the script later on, and so when I print this, it's showing me that the LoRA has been applied to the linear layer within attention, and it's also been applied to the linear layers within the multi-layer perceptron as well. So FC1 is fully connected layer. So we have this fully connected layer that will upcast to a higher dimension. Then we have a Galileo activation function, and then we have a fully connected layer 2 that will downcast it to an output dimension. And then we have the norms that are being described here. So this vision transformer, as I said earlier, I think it's got 27 blocks. So this is block 0. And if we go all the way down, which is going to take me a bit, if we go all the way down, you can see we have 26, but it's 0 based. So that means there's 27 blocks here within the vision transformer. Now, after the vision transformer, there's the vision projection. So just to show you on a diagram, we've just gone through the vision encoder here, which does the embeddings and then the transformation. And now I'm going to show you the multi-layer perceptron. So here's the vision projection. This is going to take us from input features of 1000 from the vision encoder and bring us up to output features of about 2000, which is down here as the output features. And this is done as a sandwich, as I described earlier. So first we go from 1000 to 8000, then we do a Galileo activation, and then we go from 8000 back down to 2000. And notice also how these LoRA layers have been applied. So I've applied LoRA adapters to each of the linear layers, the fully connected upcasting layer, and then the fully connected downcasting layer. I don't know if downcasting is the right word, but we're going up in dimensions and then down in dimensions. And if you move on, the last portion of the overall model architecture is the phi model for causal. So this is our language model, and this has got 24 layers, as I said earlier, 0 to 23, and it contains attention and it contains multi-layer perceptrons. So here you have WQKV, and this is to do with the attention and has LoRA applied to it as well because it contains linear layers. So down here we have the MLP. So this is the multi-layer perceptron within the language transformer. And again, we've got LoRA applied to the linear layers there. Now, just something I skirted over here is pre-processing. This is going to convert the images from whatever size they are into the 378 size that we need. And in doing so, it's going to squash any images that are the wrong size. It's going to use interpolation to get the number of pixels down to what we need. And it's also going to do some normalization. Basically, this normalization, I think, gets the values between -1 and 1 for the red, green, and blue scales. And that generally brings all of the images onto a more similar scale that allows you to train in a more meaningful way. So that brings us to the end of the overall architecture. The last portion here is the language model head. This is a series, well, not a series, it's just a linear layer that takes in the tokens, the text tokens, and converts them into vectors. Okay, so with that, we've got a look at our language model. I've actually already applied LoRA because I ran this script earlier, but here's my LoRA setup. You'll see my LoRA alpha is set to 32. My LoRA rank is set to 64. And if use LoRA is turned on, I'm going to target these models here, these modules here with LoRA layers. So I'm going to create adapters for any of the modules above that have these strings within them. And that basically gets me LoRA adapters applied to the vision transformer, to, well, all of the vision encoder, all of the linear layers, then the MLP between the vision and the language, and then within the language itself. Next, we're going to get the PEFT model using the LoRA configuration I've just described above. And this does two things. So first of all, it creates the adapters for each of the linear layers. So any linear layers that I have defined, any modules that have these strings, it's going to create these small adapters. But it's going to do a second thing, which is to freeze the base parameters. So it's going to set all the base parameters to be non-trainable. And it's going to set the LoRA adapters to be trainable. So if we didn't run this step here of getting the PEFT model, all of the parameters would be trainable kind of by default. But when we get the PEFT model, we're both creating adapters, freezing the base, and then setting to trainable only the adapters that we want. So once we've frozen the base model of, roughly 74 million, roughly 1.9 billion parameters, we've only got 74 million of those that are trainable. So the trainable parameters are about 3.85%. Now, there's an option here where you could decide to train some of the non-LoRA layers and kind of cherry pick. Sometimes you cherry pick the embed or the norm layers if you're trying to do a chat fine tuning. So this is a way that you can optionally do some fine tuning of additional parameters without training absolutely every parameter. For now, though, we're just going to focus on training the LoRA adapters. That should be sufficient, as you'll see here. Typically, before I move to the training itself, I would run some evaluation. I have a short evaluation script here that will take in a sample. It'll take in index 1 in this case from the training set and just print out the question, the answer, and then the prediction. So that allows me to gauge the performance of the model before I actually run the training. Now, when it comes to training, there's a PyTorch script that's being used here. You can't easily just drop in a Hugging Face trainer or SFT trainer because they don't have defaults for handling the images. So there needs to be some custom code, PyTorch code, in order to run the training. And that will involve running a forward pass and then a backward pass and setting up a loop so that you do that in batches. You do that over all of the data. And there is code available for fine tuning. You can check out the Moondream GitHub repo. So what I've done is based on and inspired by the code available here for fine tuning, I've just made some changes that allow me to use the LoRA fine tuning on top of that. So we'll be training for 3 epochs with a batch size of 4. I don't have very much data, so I'm not going for very big batch sizes. I'm choosing a base learning rate here, which is appropriate for a small model if you were doing full fine tuning. So you should think of this as your full fine tuning rate. Now, I'm also going to define a scaling rate, which is going to scale up the rate at which the adapter parameters are being fine-tuned. The adapters, because they have a more coarse representation of the model, you're able to fine-tune them faster than you would the individual parameters of a base model. And the way I'm calculating the scaling factor to use is using a rescaled LoRA technique, which will use a 1 over the square root of the rank in order to set the rate of training or the scale up for the adapters. If you want to learn more about this, you should check out the recent video on fine-tuning, full fine-tuning versus LoRA versus QLoRA. So with that, we're ready to move on to the full training code. There are a few steps here. We collate batches of data. We compute the loss. It's a cross-entropy loss calculation based on the predicted versus actual tokens. We define a learning rate schedule. So there's a cosine schedule here. The first 10% it ramps up, and then it will cosine decay over the rest of the 90% of the run. I've also got a constant learning rate schedule here if you just want to train for a constant learning rate. Now, after learning the data from loading the data from the train and the test splits, we can then move on to train the model. But there's one more thing I just want to highlight, which is that we need to make sure the optimizer is only doing optimization for the LoRA modules. So here, when I set up the LoRA optimizer, or rather the optimizer, I'm making sure to target the LoRA params. So this is any module within the model that has got the word LoRA within it. That's what this code here is doing. It's checking any modules that have LoRA written within it, and then it's pulling them out into a list, and we're passing this list in to the optimizer here. So that's important because otherwise you would be passing in all the parameters to the optimizer, and that wouldn't work because the gradients have been requires grad has been set to false on most of the parameters because we're freezing the base model. So if you just ran kind of the basic code here, which will allow you to fine tune the text model parameters, that's going to fail because, as I said, we've frozen a lot of the models. So we need to focus on only the modules that we've set to trainable. So with that, we can cycle through the epochs, run the forward pass, compute the loss, and then run the loss backward, which will update the LoRA adapters on the way back. Here you can see that I'm applying the specific learning rate, which is the base learning rate multiplied by the scaling factor, specifically to the parameter groups with LoRA modules within them. So that's important as well, because if we didn't make that update, the code here would just be running our base learning rate. And we don't want that. We want to accelerate the learning rate because we're using adapters which are more coarse and allow us to move more quickly through optimization. So with that, we go through the optimization. You can see a little graphic here just of the training loss falling over time and then time. So I'm getting improvement in terms of falling loss and better fitting of my eval. Here you can see the loss. That's the final training loss, the final eval loss, and just my base learning rate here. So I'm going to show you the run. Just we can take a look at how this is on weights and biases. And then I want to show you some evaluation. So here we're going to run on the test set. This is not part of the training set. It's just 3 images. So here we have a bishop and a knight. And what do you see? A white bishop and a white knight. A white bishop and a white knight is the Moondream answer. So you can see, it's using a different word, but it's getting it correct. Here we have a rook and 2 bishops. And we get a black rook, a white and a white knight. So in this case here, you can see it's not getting the exact answer correct, but it is getting the black rook correct in this case. And here in the last case, we have a knight and a rook, and it says a black knight and a white rook. So it's getting 2 out of 3 of these images completely correct, and the third one, it's making mistakes on 2 out of 3 pieces within it. But keep in mind, this is a very small model. It's only got under 2 billion parameters in total. If you look back at my lava video, I look at models that have many, many more parameters, like up to, I think, 40 billion parameters, and they're not really performing any better in fine-tuning. So I think this is really impressive what you can do with the simplicity of combining a vision encoder with a small language model and then an MLP layer connecting the two together. And also just the simplicity of taking the image and squashing it down to the pixels you require. There's no complicated image processing involved in this case, and I think it's doing very well with that kind of simple and robust approach. Now, I did say I'll just quickly show you the training. So you can see the training loss is falling here, and you can see the loss, the validation is kind of smoothly coming down here over time as the information is being embedded. So with that, once the model is fine-tuned, you can, of course, push that model to hub. It's relatively easy to do. You can just run a merge, so unload and merge. If you have the model name .unload and merge, or merge and unload, sorry, that will merge the LoRA adapters back onto the base model, and then model.push to hub will allow you to push that fine-tuned model to hub. Now that we've got a fine-tuned model, let's take a look at how we can deploy a server for that model. So I'm going to go over to the Trelis Research Advanced Vision repo, and we can take a look at the server folder. So let's just go to server here. This is a custom server that I've set up for Moondream. So it will, out of the box, only support the Moondream architecture. You could tweak it if you need to support other architectures as well. What this server allows you, there are 2 ways to make use of this server. First of all, you can just run it locally on your machine if you install the requirements, and then you can just run a dummy server so that you don't load the model, or you can run UVcorn server :app to host it on your local host on port 8000. If you don't want to run the server locally, you want to run it on a hosted GPU, you can do so using a one-click template that's in the one-click LLMs repo. That's just here. It's towards the top of the README in this public repo here, one-click LLMs. And if you click on that, it should open up the template within RunPod, and it should pre-configure so that you have an image that is ready to go. You'll see it once you select the GPU. You can even pick the smallest GPU here because this is such a small model, and you'll see the Moondream Multi-modal API has already been set up. Now let's just take a quick look at this template. There are a few environment variables that you can set. So here you would set the model ID. This will be your fine-tuned model ID. You can set a branch or revision. I'm using the base model, and I'm using the April 2nd revision. Now there are 2 other parameters to know about here. This is the batch size. So this is the maximum size of batches that will be run during inference. And you can see I've set it to 10. You could probably set it quite a bit larger, even up to 32. and it means you can process more parallel requests at the same time, although it will take up more VRAM. So if you set it really high, you will just run out of VRAM. The other thing is the batch timeout. So because this is a simple batching server, what it does is it will wait for batch timeout number of seconds, so 1 second in this case, to see if any other requests are coming in, and then it will batch them all together to do one inference. So if you want to have the lowest latency here, but not so much batching, then you would set this down to an even lower value. So once you've got all of those values set, you're ready to get up and running. And I have already got a pod that I've set up earlier. It's the one I used right at the start of the video. So you'll see here Moondream Multi-modal API by Trelis. You'll see the pod ID available here. And if you go to the README file, you'll find some instructions on how you can make curl requests to this API. The only thing you need to change is the pod ID here, the question that you want to submit, so what's in this image, and then a link to a URL for that image, which earlier on I swapped with an image of a frog. And when that's up and running, you simply grab, copy that curl request, make sure to paste in your run pod ID, and you can head over to your terminal and just paste that in. Now, this won't work because I haven't got the pod ID in correctly, but I can just replace that if you like. Let's go back over to my pod ID here. And if you copy this, I mean, I'm just copying the same curl request as I did earlier. And if I paste that in, let's just go to a new terminal. If I paste in the request there, it's going to hit the pod and come back with the description of what's happening within the image. And the real beauty of this small model is that it's so quick for inference because it's not running through as many parameters as with larger models. So you get back answers really quickly, and you get very high token generations per second. Just a few notes before I wrap things up. First off, there is a pull request if you go to vLLM for supporting the Moondream model. This will be nice because vLLM supports continuous batching. So rather than waiting for a batch to accumulate, as I've done in my simpler API approach, it will combine a portion of a completed request with a new request. And so it's able to continuously handle inputs and give improved latency on outputs. Now, the nice thing about a custom API is that you can kind of tweak it yourself to support other models, and it's simple and easy to understand, but it doesn't have those advanced features that will be a benefit when this is merged into vLLM. I will put up a one-click template for vLLM and in the one-click LLMs repo when this pull request has been merged. Just a note for those who are interested in pre-training models all the way from scratch, I think the Moondream project gives a great template for how you could include all sorts of base language and vision encoder models. In principle, you could sub out the language model with another more powerful one. Now, if you do that, the adapter, of course, is not going to be fine-tuned. It will just be randomly initialized. So I would recommend, rather than applying LoRA to the adapter, if you're pre-training from scratch, and it's not from scratch because you're using a pre-trained vision and LLM model, but if you're fine-tuning an adapter from scratch, what I'd recommend is to set all of these parameters as trainable, not apply a LoRA adapter. And then either you can freeze the vision encoder and the LLM, or perhaps my guess would be better to just apply LoRA here to vision encoder and the LLM and make the adapter fully fine-tunable. Last off, if you are training from scratch, you can take a look at the Lava Instruct dataset. I described that a bit more in my video on Lava. Or you can take a look at the new dataset, the Cauldron, which is a new source of multimodal fine-tuning data. And that's it for this video on tiny multimodal language models. If you have any questions, put them below in the comments. And as usual, you can find the resources for this video in the description and purchase lifetime access to the Vision repo at trelis.com/advanced-vision. Cheers.